Alright, so hopefully this will be the last video for this particular set of notes, but in this one I'm going to show you how to actually do orbital filling diagrams, and then I'll show you how to do electron configurations. So, a couple of hints to start out with. The Z is the atomic number, that tells you the number of protons, and for neutral atoms, the number of electrons. And how do you know it's neutral? Well, if I don't tell you it's got a charge, it's probably neutral. So, hint 2, the arrows that you see are representing electrons. So if you missed that earlier, the arrows represent electrons, and if it points up or down, those are showing you the spin, like spin up or spin down of the electrons. All right. So when we do orbital filling diagrams and write them out by hand, usually we will represent them, the orbitals, with a line. You can draw a box if you want to. A lot of times diagrams you see printed in a textbook will have a box around them, but we're just going to do lines. And then we'll label those lines with the principal quantum number and the sublevel. So like 2s, 2 for the second energy level or the principal quantum number, and s for the sublevel or the shape of the orbital. All right, and then we're going to use arrows to represent the electrons, and then pointing up or pointing down to represent the different spins. So, for example, let's do oxygen. So you look on the periodic table, oxygen has 8 protons. So following Aufbau's rule, we'll fill in the correct order. So we will fill in 1s, then we will fill in 2s, and then we will fill in 2p. And why did we stop? Well, we got to 8. And remember that Hund's rule says that we have to fill in all of the empty seats in the orbital, or in the sublevel. Remember, all the 2p's are at the same energy level, so we have to fill in all those empty seats before we can pair up. And then the Pauli exclusion principle says we have to do down paired with up. So, we'll take that. Let's do another one. So here's neon. So we got to get to 10 electrons. Again, you're always going to fill in the same order. Either refer back to your periodic table or that chart that I showed you for knowing what that order is. So pair down, 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 and then up, 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 and we have arrived at 10 electrons. Now, what you're seeing here is orbital filling, where you draw the lines and draw the arrows, but the thing that's being written down here is the electron configuration. Both things convey the same information. So orbital filling here, electron configuration here, they just show it differently. So I'll come back in a little bit and show you rules for specifically writing the electron configuration. All right. Phosphorus, so it has 15 electrons. So we'll fill in the same order, always, from the lowest energy orbitals to the higher energy orbitals. So far we are at 10 electrons, then 3s is next. We'll pair up within that orbital, and then we'll move on to the 3p sublevel, and that completes. Now we have a total of 15. So here's the orbital filling diagram, and here's the electron configuration down here. All right, potassium. So we've got to get to 19 electrons. Remember, following Hund's rule there, as we fill in all of the ones within the same sublevel, and then we go back and pair up. And we'll repeat that up here on the 3p. And then notice that we follow the Aufbau rule, and we don't fill in 3d yet because you have to fill in 4s before you can fill in 3d according to Aufbau's rule. Right, so we're going across here. This is the orbital filling diagram for the orbital notation, orbital filling diagram. We're going to do all of the second row on the periodic table. Okay, so here's lithium, and here's beryllium with one more electron. So it's like, why didn't we put it in that? Well, 2p is separate from 2s. The 2p orbitals are at a higher energy level, so 2s will fill in first. And then when you fill in these 2p's, I usually draw some brackets here to group all of these together. But anyways, when you fill in the 2p's, since they are all equal in energy, Hund's rule does apply, and you have to spread these out before you can pair them up. So nitrogen has the most unpaired electrons, and then we're on to oxygen, and oxygen will have 4 in the 2p, so you have to go back and pair one up. Then there's fluorine. Notice the correlation here, so you kind of already saw this on the previous slide, hopefully, but 1s2, so the number up here showing the number of electrons in the orbital are in the sublevel, 2s2, and then 2p5, so there are 5 electrons in the 2p. So all of these orbitals here associated with 2p are being counted when you write the number of electrons there. And hopefully not surprisingly to you, all the electrons in neon are paired up. A little bit later I'll show you how to do the shorthand or the noble gas notation for these as well, like you see on the right side of the table. All right, now when you write electron configurations, you don't have to draw all the arrows, but you do convey essentially the same information as the orbital filling diagram. So steps here, you can locate the element whose electron configuration you wish to write on the periodic table, and particularly you need to locate the atomic number of that element. Fill orbitals in the proper order, following Aufbau's rule with electrons, and also following Hund and Pauli's rules as well. And then you check to make sure that the total number of electrons equals the atomic number. All right, and recall, we've kind of already talked about this, but the S, P, D, and F blocks. So as you're filling in 1s electrons, and then, helium is here on your periodic table. We're putting it here just for the sake of making it fit in the S block. And then 2s, then 2p, 3s, 3p, 4s, and then this was the weird one, remember, 3d, 4p, 5s, 4d, 5p, 6s, and then 4f, 5d, 6p, 7s, 5f, 6d, and 7p. So if you just kind of follow the general rule with this block, that's fine. I showed you a couple exceptions in the previous video. You don't have to worry about the exceptions unless you just want to. Okay, so let's look at a few electron configurations. Start with carbon. The electron configuration of carbon is 1s2, 2s2, 2p2. So what are these things talking about? The coefficient is talking about the principal quantum number or the energy level in which those orbitals are found. Those electrons are found. The SPD or F is the shape, orbital shape, and denotes the sublevel within the energy level where those electrons are found. Remember, S has a maximum of 2, P has a maximum of 6, D has a maximum of 10, and F has a maximum of 14. Okay, and then the superscript tells you how many electrons are found in that particular sublevel. So you don't max them out. At least the last one you don't have to max out. So you fill in from the lowest energy level first, like Aufbau's principle said. Follow that order. Fill this one up, then you fill this one up, and then carbon only needs 6 electrons because its atomic number is 6, and if it's neutral, it'll only have 6 electrons. So you fill that into 2, you have a total of 6 electrons there. All right. So just to kind of go over what this is telling us, it's telling us carbon has 2 electrons in the S sublevel, 2 electrons in the S sublevel on the first energy level, 2 electrons in the S sublevel on the second energy level, and then 2 electrons in the P sublevel on the second energy level as well. So these two are on the same energy level. All right, so the outermost energy level for carbon is the second energy level, and that's known as the valence shell or the valence electrons. So there are 4 valence electrons on carbon, and we'll come back and visit that again when we do periodic properties in the next module. Now, you can use shorthand notation or noble gas notation to shorten these electron configurations, and that can be really helpful. So the noble gas symbol is going to be substituted for the electron configuration of everything that it takes to make that noble gas. And then after the noble gas symbol, you put the outermost electrons or the remaining electrons in the configuration. So, for example, by the way, we put that noble gas in brackets. So for example, if we're going to write the electron configuration for calcium, the full electron configuration for calcium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then the shorthand electron configuration, well, you go back and look and say, well, what's the noble gas that comes immediately before calcium? And you look back and you find, oh, it's argon. If you're like, hey, Mr. Benner, how do you know which ones are noble gases? Let me show you. All right, so here are the noble gases. They're on the far right side of the periodic table. There is helium, neon, argon, krypton, xenon, and radon. So those are your noble gases that you could potentially use for noble gas configuration on the periodic table. Now, and when you do the shorthand, so argon has 18 electrons. So putting AR in brackets takes the place of those first 18 electrons. And then you just write the remaining part of it, the 4s2, outside. And with the 10, so the preceding noble gas to 10 is krypton. You just look for the noble gas that has the next lowest, or the next smaller atomic number underneath whatever the atomic number of 10 is. So like 10 is 50. And then if you look, there's krypton is a noble gas with 36. Xenon is a noble gas with 54. So you'd use krypton because 54 would be too many electrons for 10. By the way, 10 symbol is SN if you're looking for it on the periodic table. All right, so once you do that, just write the remaining electrons in the electron configuration after that, and you're done. And if you master using this, it makes it really easy for you to go in and fill in those remaining electrons because you don't have to write the entire configuration if you figure out how to say you're here, and then you know, oh, I'm going to start on 5s2, and then 4d, whatever. Okay, so thanks for watching, and that brings us to the end of this presentation. Please let me know if you have any questions,